Massive waves sweeping across our planet, silently. Imagine invisible, massive waves sweeping across our planet, silently dictating our weather, from scorching heat waves to brutal cold snaps. These aren't ocean tides or seismic tremors, they're RoSSby waves, also known as planetary waves. They're vast, undulating meanders in high-altitude jet streams and deep ocean currents, and they're fundamental to understanding Earth's dynamic systems. First identified by the Swedish-American meteorologist Carl Gustaf Rossby in 1939, these waves are a critical piece of the climate puzzle. At their core, RoSSby waves form because of Earth's rotation and the Coriolis force. The Coriolis force changes depending on your latitude. This variation creates a natural restoring force, causing air and water to oscillate in these wave-like patterns. Think of it this way. Because the Earth spins faster at the equator than at the poles, any moving fluid gets deflected, creating a constant push and pull that drives these enormous planetary wiggles. RoSSby waves manifest in two primary domains, the sky and the sea. In the atmosphere, they're the large, meandering loops of the jet stream, which you often see on weather maps, even if your meteorologist doesn't call them by name. These atmospheric RoSSby waves are the weather makers. When these waves are relatively flat, weather systems move quickly across continents from west to east, but when they develop deep, dramatic loops, they can stall everything. This is what causes prolonged extreme weather events like persistent heat waves, extended droughts, or those multi-day deep freezes we've come to know, often linked to the polar vortex dipping south. These atmospheric waves move relatively quickly, shifting over days or weeks. Then there are oceanic RoSSby waves. These are the hidden giants of the climate system. They move along the thermocline, that boundary between the warm surface water and the cold, deep ocean. These waves transport enormous amounts of heat across entire ocean basins, profoundly influencing long-term climate patterns. They're also instrumental in phenomena like El Niño and La Niña. These oceanic waves, by bouncing off continental boundaries, actually help trigger the transitions between the El Niño and La Niña phases. The key difference? Oceanic RoSSby waves are incredibly slow. A single wave can take months, sometimes even years, to cross the vast Pacific Ocean, making them major drivers of our long-term global climate. So what's the physics behind this planetary wiggle? It all comes down to the conservation of potential velocity. Imagine a column of air starting near the equator and moving northward. As it heads north, the Earth's rotation beneath it appears to increase. So to maintain its total rotational energy, that column of air has to slow its spin relative to the Earth, causing it to curve back southward. But then it overshoots, heading south where the Earth's rotation appears to decrease, so the air column speeds up its spin and curves back north. This continuous adjustment creates wave. This variation of the Coriolis effect with latitude is known as the beta effect, and it's the restoring force that keeps these waves oscillating. To highlight the distinctions, atmospheric RoSSby waves operate in the air, impacting daily weather and extreme events over days to weeks. Oceanic RoSSby waves, however, move through water along the thermocline, influencing long-term climate and events like El Niño over months to years. While atmospheric waves determine if you'll need an umbrella next week, oceanic waves are dictating whether global temperatures will spike next year. Understanding RoSSby waves is absolutely crucial for both short-term weather forecasting and sophisticated long-term climate modeling. There's a growing concern among climatologists that as the Arctic warms faster than the rest of the planet, a phenomenon known as Arctic amplification, the temperature difference between the equator and the poles is shrinking. Many believe this is causing atmospheric RoSSby waves to become slower and much more amplified, potentially leading to more frequent and intense extreme weather events. If you found this exploration of planetary waves insightful, share this episode with someone who loves uncovering the hidden forces that shape our world.